we're going to start our next section. And before I tell you what it's called, we're going to do a little practice with derivatives just so we remember. So I have this little problem right here. We want to know the derivative if our equation is y equals e to the x squared over 2. So in case you forgot anything that's e, you start by keeping it the same. So we're going to have e to the x squared over 2. But then since it's not just e to the x, we have to do the derivative of the exponent, which I'm going to pull that over 2 out and make it a 1/2. And then the derivative of x squared is 2x. And then your 1/2 and your 2 cancel. So in the end, you get, when you're done, you just have this x left. So it's x times e to the x squared over 2. So there's a little derivative practice in case you forgot. And if you look at that, you should notice that the derivative was the same as the original function, that y, just with a multiple of x in front, right? Here's my original equation, e to the x squared over 2, and my answer, my y prime, if we look here and here, my derivative is just the same thing but with an x in front. And that would happen no matter what, like if it was 2 of those or 3 of those, right? That would be true for any multiple of y. So this is actually called something fancy. It's called a differential equation. So when you do a derivative and you get in the derivative, you get your original function just multiplied by some x, that's called a differential equation. And that is a whole class in college. There's a whole math class called differential equations. If you're going to be a math major, you'll probably have to take it. Some people think it's hard. I thought it was easy and fun. I don't know. I liked it. But so the section that we're going to do, our next kind of grouping of stuff, is the beginning of this differential equation jazz. Okay. So just for definition purposes, a differential equation contains an unknown function and its derivative, or maybe a multiple of its derivative. Okay. So if you need to pause and you want to write that down, go for it. A lot of these differential equations are hard to solve. So we're going to focus on the kind that can be solved, and the kind that can be solved is this thing called a separable differential equation, right? And so what that is we're going to have our derivative, which you can use y prime, or in case you forgot, that's the same as dy dx. And that will equal x times whatever our original function is. So let's just say our original function is y. It might not be just y, but let's just say it's y. And the reason this is called separable is because what we're going to do is we're going to separate this dy dx, and what we're going to do is we're going to get all the y's on one side of my equation and all the x's on the other side of the equation. So we're going to split up this dy dx. So somewhere we'll have a dx, on another side of the equation we'll have a dy, and we're going to separate it. And what we're going to do is we're just going to solve for y. Okay, we're used to our equations being y is a function of x, so y equals something with some x variables. So what we're going to do in these is we're going to separate the derivative, the dy dx. We're going to separate it into y's on one side, x's on the other side, and then we're going to solve for y. Okay, so the reason it's separable is because you can factor your derivative into x times the original function. So that's why it's called a separable differential equation. You can't always do that, but in this special kind where you can make it an x factor and the original function factor and you can separate them, it's called separable. And this sounds like long and hard and complicated, but really all we're going to do is get the y's on one side, the x's on the other, and then solve for y is what it comes down to. So we're going to start with this one, and it's kind of blurry, so I'm going to rewrite it. Hold on. we got dy over dx equals x squared over y squared. And then I'm going to get rid of this. Okay. So think about what this means. dy dx is y prime. So there's some function whose derivative is x squared over y squared. And I don't know about you, but I don't really want to know what that equation looks like because I feel like it's going to be gross, right? Like this is a gross enough looking derivative as it is. The equation it came from cannot be that pretty. But we're going to try and we're going to solve for y anyway. So here's what we're going to do. The first thing I'm going to do, my goal is to get y is on one side and x is on the other. So I want to get rid of this dx and I want to move it to the other side. And the way we're going to do that, since it's divided, since it's dividing something, it's on the bottom, you know the opposite of division is multiplication. So we're going to multiply both sides of our equation by dx. Yes, you can do that. You are allowed. So this dx and this dx will cancel. So now we have dy equals x squared over y squared dx. Okay. And my goal is to get all the y's on one side of the equation. So I need to move this y squared. Right now it's on the bottom, it's dividing, so now I'm going to multiply both sides by y squared. Because the y squared here will cancel a y squared here. Oh. So now we have y squared dy equals x squared dx. Okay, so I have x's and y's on the same side. Great. That was my goal. Now I need to solve for y. And the way we're going to do this is with an integral, okay? The dy and the dx means this is, derivative, so you undo a derivative with an integral. So now what we're going to do is we're going to do the integral on both sides, okay? And let's see, you do your add 1 and divide by it rule. So this would be y cubed over 3 plus c. Remember, it's generic, so you need a plus c at the end, and then equals. And then you do the rule on this side, add 1 and divide by it. So x cubed over 3 plus c. And you're like, uh-oh, we have two c's. It's easy to fix. Make one of them c1, one of them c2. Okay? Easy. So now, let's see. I wonder if I can move this. Oh, hide. Okay. Okay, we're trying to solve for y. So, the first thing I'm going to do is I'm going to subtract my c1. So now I have y cubed over 3 equals x cubed over 3 plus c2 minus c1. And remember, these c's are constants. So right here, instead of writing c2 minus c1 every time, I'm just going to change it to a c. It's just a different number. It's still a constant. So I'm just going to make it say c. Okay? And honestly, this is what I do most of the time in this step. So like if I was doing this just, just for myself, I would do, I would write y cubed over 3 equals x cubed over 3 plus c, and just skip to this step right away and just call it a day, right? We know that each of these, when you do a generic antiderivative, has a plus c at the end, but since we're solving for y, we're going to move one of those c's over, and it's just going to turn into a different constant. So I'm just going to put a plus c at the end and call it a day. And remember, when you do an integral, the dy goes away, or on the right side, the dx goes away. Okay, so now we're solving for y. All right, we can do this. That's not hard. Okay, so I got a 3 on the bottom. I'm going to multiply everything by 3. So now I have y cubed, because those cancel, equals x cubed, because those cancel, plus 3c. And then I need to do a cube root, because that is how you undo a cube. So we need to cube root both sides. So we got y equals the cube root of x cubed plus 3c. You solved for y. Done. The end. Good job. Lovely. Put a box around it. Great. Done. Okay, so we solved for y. So in general, the gist of all of these will be get your dx on the same side as the x's, get your dy on the same side as the y, however you accomplish that, as long as it's algebraically legal, it doesn't matter. And then do an integral on both sides. Do your plus c, and then solve for y. Hooray, you solved a differential equation. Great job. Now, technically, that solution is called a general solution, because we had like y equals cube root x cubed plus 3c. Depending on what this c is, that's going to give us different equations that will graph differently. They'll all be related, but they'll also all be slightly different. Okay, so this is a general solution. Anytime you have your C still in your answer, that's a general solution. Now, however, right, let's say that I took this equation and I wanted to find the solution that satisfies y of 0 equals 2. Okay, so then we would say, all right, that means y is 0, that's where x is 0, equals 2. So we would have 2 equals the cube root of 0 cubed plus 3, see? So we got 2 equals the cube root of 3c. And so we could cube everything. Now we're solving for c. We're trying to find the specific value of c that makes this constraint true. So now we could cube everything. Cubed. So we got 8 equals 3c. All right. So then what we could say is we could say y equals the cube root. I'm going back to this original equation. X cubed plus, but instead of 3c, we could put 8 right there. And this would be a specific solution that satisfies that y of 0 equals 2 deal, right? So when you just solve and have your C in the answer, it's called a general solution. If I give you some kind of constraint or value that your equation has to satisfy, then you're finding a specific solution.